All right. Suppose you have this carnival game. I think we have it at our fair as well. So let's say you have a 1 yard by 1 yard square, so 36 inches by 36 inches, obviously not drawn to scale. And then what you're going to do is you're going to randomly toss a coin, and let's say we toss a quarter in there. And let's assume that the diameter of the quarter is 1 inch. I'm not sure exactly what the diameter of a quarter is, but let's just assume it is. If this quarter randomly lies in this region here, what is the probability that it will land in like a target region? Right? We have a game like this at the fair, right? Except you might be tossing dimes or something. Why don't we just assume we're tossing quarters though? Now, how big do you want to make this target area? See, because what you're trying to do at a carnival or a fair is you want to try to make as much money as possible for your class, right? Because like the junior class, don't you guys usually do malasadas? Yeah, but if you do a game like this, you probably gonna get more money. Is anybody like on the malasada committee? Nobody. So what happens is you work in the I don't think there's a malasada booth this year, or is there? On Friday. No malasada booth. Anyway, what you're doing is you're working there, and they're gonna take the money that they make from the malasadas and put it into your account, so you can use it for like senior camp or whatever. When you're a senior, or apply it to your dress or suit, whatever. Yeah. So I've been told in the past that usually you get like $100 something put in your account, but maybe you can make more money by doing something like this. So how big do you want to make the target? See, if you make the target too small, like the one in our game, it's really hard, the target. You guys know what I'm talking about? I don't know if they're going to have this game on Friday or not. But then if you make the target too big, then you're not going to make that much money. So what do you think a good target would be? Let's make it simple, a square. Okay, one class did 3 by 3, the other class did 4 by 4. Let's do something different.
2.
You want to go 5 by 5, or you want to go down 2 by 2?
2 by 2.
2 by 2. Because if you make it too small, then people might not want to play this game. You want to make it enticing enough so a lot of people play this game. And then what kind of prizes are we going to have? A giant doll. That's always good, yeah? So let's say we have gigantic dolls or stuffed animals. Wait, how does this work? Right? So this is what you're gonna win. So, assuming we buy this doll from somewhere we can get it really cheap, where are we gonna get it from?
Ross.
No way, Ross. That would be too much. Like I'm talking about, we want to get like hundreds of these. I'm thinking Mexico, China, Taiwan. I don't know. Anyway, the other class said, what would the cost of a doll like this be? If you made it in China or whatever, Mexico. $1? This is big, you know. This is actually gonna be twice the size now.
2.
Or maybe it could be this size. I don't know. I think it would be more than $1, but the other class said maybe $2. Because you gotta think, they're gonna make it out of the cheapest material possible, right? In fact, the stuffing might be flammable materials too, right? You just don't know. So the other class thought about $2 is reasonable. Plus you gotta pay for shipping, right? So let's say that a doll like this costs $2. I have no idea what it is. Okay, so what is the expected value if somebody comes to play this game and randomly tosses a quarter into this region? What is the probability that the quarter will fall into this region? Now, don't make this mistake on the test, because this would be yeah.
You can only see half the doll.
I forgot we were videoing again. Here, let's try. There. Now you can see the doll. Okay, that's good enough. were to randomly toss this coin into this region, what's the probability that it's gonna land in this region? Can I just take the area of this, which is 2 squared, and divide it by the area of the whole thing, which is 36 squared, and just divide it? No, this would be a fatal error. And you're thinking, what? No, that's it, Mr. Burke. No, that's because a quarter has an area to it. Like if you were throwing darts, a dart is like a single point, right? You can think of it as a single point. Then if you were randomly throwing a dart in here, then you can go this area divided by that area. But you're tossing a coin which has area. So you cannot do that. So what do? You think of the center of the quarter. Where does the center of the quarter have to land so that it lands completely in this region? So you gotta reduce it down to a point. So think about it. If the quarter has a diameter of 1 inch, here's the center of the quarter. Where does the center of the quarter land so that it's in this region here? The center of the quarter then has to lie in this smaller square. And what are the dimensions of that smaller square? 1 by 1. That's right. So it's actually 1 squared. I'll just do this. Don't do this. It's actually 1 squared over, and same thing over here. If it's going to fall into this, it has to completely lie in the region. So the center of the coin has to land in this box. And what are the dimensions of that box? 35 by 35, so 35 squared. So everybody understand that? You gotta look at the center of the coin, that's the key. This problem is on the test now. Okay, so this is the probability of winning. Now the thing is, you gotta randomly toss a coin in here, right? Because what happens if you start aiming? Then it's not random anymore, right? So people are gonna try to get close to the table, they're gonna reach over and try to aim it. So what can you do to make it more random? Like people gotta stand a certain distance away, so you just make sure that they stand, if it's really close, then it's easy to aim, but you make it farther away. And then what's another thing you could do to make it more random?
Catapult.
Catapult?
Make them like not be able to toss it.
But then that's the theme of the game, right? Toss the coin, win a prize. You make the table really slippery, that's right. Like if you had grip on it, like for example, a carpet, then it's easier to aim it, right? So you gotta make sure it's very slippery. So you gotta make sure all the conditions are there, so it's as close to random as possible. So if this is the probability of winning, then what's the probability of losing then? 1 minus that, so 1 minus 1 squared over 35 squared. So here's the probability of winning, here's the probability of losing now. Which expected value are we gonna do? When do we do the expected value for the person then? So, if this is the probability of winning, I need to multiply that by how much you're gonna win. How much do you win?
2.
And then come on, you guys did already this homework. This stuffed animal costs $2. How much did you actually win? It wasn't last night's homework, but you did it.
How much is the game?
$1.75 you won. How come? Because, okay, when you win, they go, oh, here's your doll and here's your quarterback. Do they give you your quarterback? No, they don't give you your quarterback. That's why you only won $1.75. That's important to do now. That would be like a 3 or 4 point error right there. And then, what happens when you lose? You lose your quarter. So it would be negative 0.25. This is your expected value for this game. Okay, somebody compute this on your calculator. Come on, we can have a short class today, because there's no homework tonight, study for the quiz. Plus, we're gonna go over quiz questions as soon as we finish this. So we're not moving on till somebody computes this. Give me 5 decimal places. Don't make me do it on my phone. take a long time. Yeah, maybe I should race you. Let's see. Menu. Shh. Calculator. You know what? I don't want to do it. Negative 2. 4. One more place. So 4 then. 4, 4. Okay, 2, 4. Okay, give me 6 decimal places. 0.248. Okay, can somebody confirm that? Okay, so that means every time you play this game, you're expected to lose this much. So in other words, if this game was played 1,000,000 times, probably the people would lose $248,367. But then that's the money that you would make for your class. Now how many, so in class of 2022, how many people in the graduating class? Oh no. 260. Okay, so what is $248,367 divided by 260? Okay, this is easier to do. This is how much each person would get put into their account. You can use it for senior camp, whatever, graduation. Can you apply this kind of stuff to books and stuff too? Who knows this kind of stuff? I don't know. Okay. 955. Okay, that's good enough. So, would you rather do the Malasana booth and you get $100-something put in your account, or you would rather play this game and get $955? I don't know, that's easy to me, but then we made several assumptions, right? This game was played 1,000,000 times. Do you think this game could be played 1,000,000 times? Why not? On a normal fair day, right? You got Friday and Saturday, and it's open, what, like 10 hours or 11 hours? Well, why would it? Well, if you just had a single table like this, it would be kind of hard to be played 1,000,000 times, but then. So what you want to do is you get a big tent, like the tent right there, and you get the table filled with lots of, no, this is what you gotta do. You gotta have like lots of these smaller ones in there, like that, under the big tent. And you gotta advertise. So the tent is over this, and then, well actually you would even have more than that. And then you gotta have these dolls, like they're hanging from the rafters, right? Like that. And then people go, yeah, I wanna win that doll. So then one person, you don't want one person to play just one time, you want one person to play multiple times, right? So yeah, I think it's conceivable that the game could be played 1,000,000 times. Not 1,000,000 people, but some people gonna play it like 100 times, right? Because they want to win this darn doll, that's why. Anyway, so the one that you're gonna see on the test is, I'm gonna give you a, probably gonna be a square region. But then last year I changed this over here. I changed it to an equilateral triangle. I just tell you now, you're just gonna get a different shape. So think about it. If you have an equilateral triangle, and then you have a coin, where does the center of the coin, so let's say this is a 4x4x4 equilateral triangle, just to show you the thinking that's involved, because it's not as simple as you think, you know. Where does the center of the coin have to land so that it lies completely in the inner equilateral triangle? Is it 3x3? Well, I'll tell you what, last year a lot of people thought it was 3x3, but no, Moose Breath, it's not 3x3. What is it? How come it's not 3x3? The answer is, it rhymes with geometry. Geometry! How would you figure that out? Because once you know the side of the equilateral triangle, I hope you guys remember the formula. It's going to come up a lot in calculus as well, I told you this. What's the area of an equilateral triangle if you know the side? Plus it's on the SAT cheat sheet. I didn't look at that page, Mr. Park. Root 3 over 4 times the side squared. I'm going to tell you, this formula is golden. Please don't forget it. It's going to come up a lot in calculus. Here, this is what we do in calculus. So let's say you have a region bounded by y equal root x, and then let's say x, y equal x over 2. Okay, here's a region. So there's a three-dimensional surface up here on the top. Every time I take a cross-section perpendicular to the x-axis, the cross-section is an equilateral triangle. Can you imagine what that thing looks like? So this is the base of this solid. Okay, so it's like there's a three-dimensional solid over here. So you put it on the cutting block. If I remove a slice that's perpendicular to the x-axis, you're going to see an equilateral triangle. So like over here, you would have a smaller equilateral triangle, but then over here it's bigger. And then like if you slice it over there, then it gets kind of small. But every time you do it, it's an equilateral triangle. Can you imagine what shape that is? That's what you got to do in calculus. I'm not getting any response. Why is that surprising? Here, let me show you a different angle. Let me see if I can draw it. Okay, so every time you slice it, you're going to get an equilateral triangle like this. See how the equilateral triangles are getting bigger? That's because this is wider over there. And then now, it's getting less wide. There. What does that look like? A slug, right? Find the volume of that slug. That's the kind of problems we do in calculus. But anyway, that's why you gotta remember this formula. Because if you cannot find the area of this slice, then you can't do the problem. The calculus part is actually easy. This is usually the hardest part. Anyway, so, okay, you're in a Turkish prison. You're on the test. How do you find the side of that? If this is half an inch. If this is half an inch, right? Gotta be half an inch from the edge, right? How do you figure out the side? Because if you know that side, you can use this formula. What time is this class? 9:15. Okay, this is taking way too long. How do you do it? Okay, here, I'll give you a hint. You gotta figure out this. So if this is 4, is this half an inch? No, that's not half an inch. This is half an inch. This is half an inch. So I know 4. If I could figure out this and this, then I subtract it from 4. That's how I get the side. So how do I figure out this? I'll give you a hint. Draw this in. What kind of triangle is that right here? Yeah, I know it's a right triangle, but a little more specific. It's a 30, 60, 90. That's how you figure it out. Because look, if this is half an inch, which one is 30? Okay, I'll just type. Let's blow it up then. How do I know that's the 31? Because that's 60, because it's equilateral and then you're bisecting it, right? So if this is half in a 30, 60, 90 triangle, what? If the short leg is 1/2, how do I figure out the long leg? You multiply it by √3. See, so this is actually √3 over 2, and that's √3 over 2. So therefore, what is the side of the equilateral triangle? It's 4 minus 2 times √3 over 2, which is just 4 minus √3. So then you just go √3 over 4 times the side squared. That's how you figure out the area of that. That was last year. So now that I told you this, what am I going to put on this year then? Hexagon? Octagon? Yeah, I guess you'll have to take the test to find out. Okay, anyway, this problem is on the test. I'll just leave it at that. So what do you have to remember? The center of the coin. Where does the center of the coin have to be? That's how you gotta think. All right, tomorrow we have a quiz. I figured we'd just go over some practice problems then. So the quiz is covering probability 3 and 4. So what is 3? That was binomial probability. Okay, I don't need to look at the thing. It's binomial probability. Okay, so I already wrote the quiz this morning, so I know what's on there. Okay, so let's say I'm going to toss a coin, but see, like remember I told you, what if the coin is not fair? So I'm going to tell you, tomorrow the coin is not fair. The probability of, when you toss a coin, the probability of getting a tail is, I don't want to make it, how about 3/5 then? Which of course means the probability of tossing a head is 2/5. therefore 1 minus P is the probability of a failure, 2/5. And then you just plug it into the formula. Do we remember the formula? I will after I study tonight this part. 8 choose 5, 3/5 to the 5, and then 1 minus 3/5, now let's just put 2/5. 2/5 to the 3. How come? Because these two numbers gotta add up to 8. Right? And there you go. You write that on your paper, you get 3 out of 4 points. Now, can you compute that? That's a whole nother story. That's up to you. So, yep, there'll definitely be a problem like that. But remember, on probability 3, the last 3 problems were review. So you're gonna get problems like that too. So there's let me scroll down so I can actually see it. Oh, there was only 2 other problems. Card. Okay, here, let's do one then. I think I got one of each on there. Okay, let's use the word logarithm. Logarithm. Okay, using the letters of the word logarithm, it says 3 letters are randomly selected. Let's say 5 letters are randomly selected. 5 letters are randomly selected. I don't like logarithm. Can I change the word? Let's do logarithms. Yeah, I like that better now. 5 letters are randomly selected. What is the probability of, what is that over there? Getting 3 consonants. Consonants. How do you even do this problem? This is exactly like a card problem, except the deck only has 10 things in it instead of 52. So you can remember there's 2 ways of doing it. You can think of it one at a time, which means you better multiply by the number of different orders, or you can think about pulling out 5 at once. Okay, let's do it both ways. Let's do the combination way first. If I just randomly, I got these 10 letters in a bag. I'm gonna reach my hand in and just pull out 5. What's the denominator gonna be? 10 choose 5, right? Now, I want 3 consonants. So, how many consonants are here? 7. How many ways can I select 3? 7 choose 3. That's your answer. You know what? That's too easy a problem. I'm gonna change it. Let's change it to, oh no, 3 consonants. That's good. Why did I even change it? I don't know. Okay, but then that means the other 2 have to be vowels. How many vowels are here? 3. You guys gotta be able to count, you know. Out of the 3 vowels, how many ways can I select 2 of them? 3 choose 2. There, that's your answer. 3 out of 4 points right there. Okay, but the other way is you pull them out one at a time. But there's an order when you do it that way. That's the permutation way. So, what do? Hello? Do a specific case. What's a specific case? Consonant, consonant, vowel. Okay, what's the probability of pulling out a consonant? Really? 7 out of 10. Now another consonant.
6 out of 9.
6 out of 9. Another consonant.
5
out of 8. Now a vowel. 3 out of 7. And now another vowel.
2
2
out of 6.
out of 6. Okay, but that doesn't earn you anything. That's because you did the permutation way. Now you need to multiply it by the number of different orders, because this is the only way you can get 3 consonants and 2 vowels. No, so how many 5-letter words can you make?
5 factorial.
5 factorial over 3 factorial, 2 factorial. Or you can put 5 choose 3, you can put 5 choose 2, or you could count it by hand and get 10. I don't care how you do it, that number gotta be 10 in order to get points. See, that's why, if you do it this way, then you don't have to worry about that. Right there, boom. That's 3 out of 4 points already. But see, if you did this, you didn't get anything yet until you put this here. But it's up to you. It's up to you. I'm not gonna tell you what to do. You just gotta remember, if you do the permutation way, you need to multiply it by the number of different orders. Okay, and then, I think there's only 1 or 2 problems on the next one, which is, wait, what time is this class at? Okay, we got time. conditional probability. Okay, let's do a problem. Okay, let's say you have a spinner. The spinner has 4 numbers on it. 1, 2, 3, 4. Okay, it's like this. Okay, so you're gonna spin it. Okay, if an odd number comes up, you're gonna reach into jar A and pull out a marble. But in jar A, let's see, there's 3 red and 2 blue marbles. Okay, if 2 comes up, you're gonna reach into jar B. Here's jar B. Jar B contains 4 red and 1 blue marble. If a 4 comes up, you're going to reach into jar C, which has 4 red and 3 blue marbles. So here's the question. If a blue marble is obtained, what is the probability that it came from jar, and it really, I don't really care which one it is, pick one, A, B, or C? C. Okay, how do I start this problem? Remember, what's the formula for condition of probability? I don't know, I'll know tomorrow morning. Hello? The probability of B knowing that A occurred is equal to the probability of A and B divided by the probability of A. So what you have to do is you have to read this sentence and be able to translate it to this. So if I read this sentence, what is it? Is it the probability that you get a blue marble knowing that it came from jar C? Or is it the probability that it came from jar C knowing that the marble is blue? Which one is it? Because you picked the wrong one, you know what that is, right? Fatal error. Which one is it? The second one. Do not do this. And again, what did I tell you? What is the probability that, because look, what does this mean? This is the probability that this given, or if that. Probability of, see, look, what's the probability that it came from jar C? So whenever you see this phrase, whatever comes after it, that's this. If, this is like if. If, see, if the marble is blue. That's how you tell. I'm not going to try to trick you. So, according to this formula, come on, let's quickly do this. This is the probability that, can you follow it? Look, B is that, A is that. Plug it in. Blue and it came from jar C divided by the probability that the marble is blue. Now, how do I figure out these things? What do? We make a probability tree. Okay, so when I spin this thing, what can happen? 3 things are going to happen. So let's just do the tree over here so it's on the video. So either you're going to get an odd number, and what's the probability of getting an odd number? When I spin this spinner? 1/2. And then if I spin a 2, what's the probability of getting a 2? What's the probability of getting a 4? Okay, and then? Okay, now if I reach into jar A, only 2 things can happen. It's either red or blue. What's the probability of getting a red? 3/5, and then blue would be 2/5, okay? And what about from jar B? Red or blue? 4/5, 1/5. And then red or blue? Jar C? 4/7, 3/7. Okay, now let's compute this thing. What is the probability that the ball is blue and it came from jar C? That would be here. It came from jar C and then it's blue. So it would be 1/4 times 3/7. divided by the probability that the ball is blue. But there's 3 ways the ball could have been blue. You could have gone to jar A and pull out a blue marble, or you could have gone to jar B and pull out the blue marble, or you could have gone to jar C and pull out the blue marble. That's the way I did it on my written solutions anyway, right? So what's the probability of these 3 things happening? 1/2 times 2/5 plus another way that you could have got a blue marble would be this and that. So 1/4 times 1/5 plus, and then finally 1/4 times 3/7. Once you write this on your paper, you get everything except 1 point. And then can you compute this for 1 point? Well, we'll have to see tomorrow. Anyway, this is how you do conditional probability. It's not that difficult. You just gotta practice it a few times. That's why